Hi, welcome to Tom Science. Today's topic is about effect of intercooler on gas turbine engine. We know that intercooler is placed between two compressors if it is two stage. If it is multi-stage, we will be having multiple intercoolers. What is the purpose of intercooler? Intercooler is a device which used to reduce the temperature of air that is coming from the low pressure compressor. Why we need to reduce the temperature of air? That is the today's lecture. In general, any engine we concentrate on two parameters, that is efficiency and net work done. In this lecture, we are going to look at what is the effect of intercooler on net work done and efficiency of gas turbine engine. For that, I have taken two problems. One problem without intercooler, the other problem is with intercooler, but 100% same parameters. Let's look at first problem. A simple constant pressure gas turbine plant draws air at 30 degrees Celsius. Draws air at 30 degrees Celsius and compress it through a pressure ratio of 6. That is P2 divided by P1 is equal to 6 RP. Then air passes to the combustion chamber. After combustion of fuel, gases enters the turbine at a temperature of 787 degrees Celsius and expand to the initial low pressure. Calculate the net power output of the plant per kg of air. This is our first problem. This problem already we have solved in previous lecture from this playlist. If you have any doubt how to solve this problem, kindly go through it. The next problem is a gas turbine plant consists of two-stage compression, that is LP compression and HP compression with perfect intercooler. So here we are going to take perfect intercooler. What is meant by imperfect intercooler, that we will see in next lecture. And a single stage turbine. If the plant works between the temperature limits 30 degrees Celsius, that is T1 30 degrees Celsius, then 787 degrees Celsius, that is after combustion. Parameters are same for previous problem and this problem, and pressure limits of 1 bar and 6 bar. So 1 bar ambient, 6 bar high pressure compression. Find net power of the plant per kg of air. Now let's solve the problem. First we will see without intercooler, T1 given in question, RP given in question, T3 given in question. We found out T2 and T4 with help of isentropic compression. Similarly, compressor work, turbine work, heat addition, heat rejection. All this we found out, and finally net work done and efficiency. In previous lecture, if you have any doubt, just go through it. Now we look at with intercooler. So in with intercooler, we have to know one thing, because we have two compressors. Compressor 1, compressor 2, 1 to 2, compressor 1, 3 to 4, compressor 2. We know what is our P1 1 bar. We know what is our P4, that is 6 bar. Then what about P2 P3? For that we have to use this relation. P2 is equal to root of P1 into P4. This relation next class I am going to derive. I am sorry for that. So P2 becomes 2.45 bar, which is nothing but P3, because in heat rejection intercooler we have constant pressure heat rejection. P2 is equal to P3. So 2.45 bar if it is perfect intercooler. Remember all this. Now we will discuss about LP compressor, that is low pressure compressor. From isentropic relation, T2 divided by T1 is equal to P2 divided by P1 whole power gamma minus 1 divided by gamma. P2 divided by P1 can be written as RP, that is pressure ratio. This equation can be written as T2, we need to find out, T2 is equal to RP whole power gamma minus 1 divided by gamma into T1. RP we know that is 2.45, because P1 1 bar, gamma 1.4, T1 given in question 30 degrees Celsius, convert into Kelvin, that is plus 273 will give 303 Kelvin. Then T2 becomes 391.4 Kelvin. So in low pressure compressor we need to find out the amount of work given to the compressor, that is WC1 Cp T2 minus T1. This equation we derived in previous lectures. Just to go through it, how to apply the steady flow energy equation for the compressor. Then WC1 becomes 88.85 kilojoule per kg of air for one compressor. Next you will see a second compressor, that is 3 to 4. So from isentropic relation, T4 divided by T3 is equal to P4 divided by P3 whole power gamma minus 1 divided by gamma. We know P4 is 6, P3 is nothing but 2.45. So T4 can be written as Rp whole power gamma minus 1 divided by gamma into T3 because Rp is same because it's a perfect intercooler. Then T4 becomes 391.4 Kelvin. If it is perfect intercooler, the T2 and T4 will be same always. Similarly, what is the work given to the compressor 2? That is Cp T4 minus T3. Your WC2 will become same 88.85 kilojoule per kg. If it is perfect intercooler, these both will come same answer. Don't forget it. Now let's see what is the total amount of work given to the compressor. That is WC1 plus WC2. So WC becomes 177.7 kilojoule per kg of air. Whereas without intercooler, you can look at here 203.41 kilojoule per kg of air. What it means? If you use intercooler, it will reduce the work given to the compressor. So that W net will increase. See, 248.92 kilojoule per kg to 23.21 kilojoule per kg. But efficiency will come down. What is the reason for that? Because when you reduce the work given to the compressor, automatically heat supply to the combustion chamber will increase. That is 671.94 kilojoule per kg. Look at here, 557.37 kilojoule per kg. We are taking turbine work output is same for both the problems. Conclusion of this, when you use intercooler, the work given to the compressor will reduce, which result in increasing of W net, that is net work output. But efficiency of a Brayton cycle will never be increased when you use intercooler because of QS will increase, that is heat supply to combustion chamber will increase when we use intercooler. If you like this video, kindly like, subscribe and share. In next lecture, we will see what is the difference between perfect intercooler and imperfect intercooler. Thank you.